Welcome to the Digital Experience by MAPEI. These webinars are intended to be interactive, but for the purpose of time, your questions can be posted in the chat box. The presenter will address a question and the answer at the end of the session. The presenter's email contact information will also be provided at the end of the session if you prefer to reach out to them directly. Here's some information about today's presenter. Rankin Jays is the coatings business development leader for MAPEI's concrete restoration systems line. After immigrating to the United States in 1997, Rankin worked with Parker Paint as director of channel sales and marketing, covering the Pacific Northwest market. When Parker was acquired by the Comex Group in 2005, Rankin transferred to Color Wheel Paint in Orlando, where he remained as national product director until 2001. He then spent several years with Stowe Corporation in Atlanta as product marketing manager for the company's coating division. Rankin has been in his current role as business development leader with MAPEI since 2015. Rankin holds a BS in psychology and a master's degree in business administration from universities in New Zealand. Please silence your phones. We appreciate your attendance. Here is Rankin Jays.
Thanks, Princess. Appreciate the introduction, and good afternoon, everyone, or good morning, depending on where you might be. Thank you for attending today, and welcome to this webinar. It's entitled Concrete Deterioration and Impact on Coatings Performance and Design. And we'll just get the slides moving here. Okay. What we're looking at today is the reviewing the types and causes of concrete deterioration and develop an understanding of specific features of coating technology to improve the durability and lifespan of concrete structures. Want to take a look at the environmental and service-related causes of concrete deterioration and the effects that they have on the structure. We'll understand the objectives behind specifying protective coatings for concrete and the potential contribution they have on environmental and economic sustainability. We'll also identify specific performance measures of coating systems and understand how these can counteract the environmental effects of concrete deterioration. And lastly, I want to compare some specific data points to assess the absolute and relative performance of coating systems, both in theory and in practice. So jumping into this, I want to start with a couple of concrete basics and understand that concrete is the most widely used man-made product in the world. The concept dates back to ancient times, obviously, but it wasn't until the 18th century that the use of hydraulic lime was actually pioneered. Traditionally, it's a very simple cement mixed with grated aggregates and water. It's now a much more complicated concoction of chemical reactions with admixtures to ensure durability and longevity. The advantage concrete has is it's relatively low cost, great stiffness, excellent compressive strength, relatively easy to fabricate with. It's non-flammable and is a very stable substrate. On the downside, however, it has very low tensile strength. It is brittle and lacks long-term durability, and that's somewhat of a relative term. We see concrete structures standing for centuries, but as we get into this, you'll see what we're talking about in terms of deterioration and how that it does impact that comment about long-term durability. So concrete hardens through the process of hydration, and during the curing process, calcium hydroxide is formed, creating a very high pH condition within the concrete. It forms a passive layer around the reinforcing steel that retards corrosion. But sooner or later, defects that define deterioration will start to appear. Concrete structures deteriorate with time and much faster in extreme environments associated with high humidity, presence of chlorides, CO2 in the atmosphere, wet and dry cycling. Ingress of damaging substances takes place through the pores of the concrete by the process of diffusion, and that really starts to initiate the corrosion of the reinforcing steel. Onset of corrosion of the steel is accelerated when that high pH condition, or that passivating layer around the reinforcing, is destroyed by reducing the alkalinity within the concrete structure or within the concrete matrix itself. So that then the steel corrodes, then creates a concrete spall, and that ultimately reduces the strength, aesthetics, and integrity of the structure. So that's pretty much it in a nutshell. But the components of deterioration generally fall into 4 camps: chemical deterioration, physical, mechanical, and then defects that might be entrained during installation or as part of the design mix. So we'll take a look at some of those. Carbonation is the first one, and that occurs when CO2 present naturally occurring in the atmosphere penetrates the concrete and reacts with the calcium hydroxide in the concrete, and that produces calcium carbonate, or it essentially turns the concrete to chalk. The reaction reduces the pH of the concrete pore solution, destabilizing that passivating layer. Carbonation is generally a very slow process and depends greatly on relative humidity, temperature, and overall concrete quality. There's plenty of predictive models out there, including accelerated carbonation tests simulating variable factors responsible for acceleration of carbonation. But the one that really puts it in fairly simple terms for me is actually this Brown's equation that says we take, let's say, 5,500 psi concrete, a carbon under normal conditions, a carbonation wave front will extend into concrete just under 1 inch, 7/8 of an inch, in a period of 20 years. Okay, so it is slow, but and if that was the only thing that happened to concrete, yeah, it would, that's a fairly durable life cycle of a concrete structure. But we're talking about a cumulative effect of a number of other deterioration effects as well. Sulfate attack occurs when naturally occurring sulfates of sodium, calcium, magnesium can be found in the soil and groundwater. And as soluble ions, they're carried into the concrete matrix by water. That reacts with the hydrated compounds in the hardened cement and expand, and that can produce sufficient internal pressure that it can cause a loss of cohesion and strength. Concrete exposed to a higher frequency of wet and dry cycling and porous concrete's much more at risk. Chloride ingress. Two-thirds of our population actually live in coastal states. 1/3 of our population actually live in coastal counties. So, they're a very aggressive environment with the salt-laden sea air. And chloride ingress is really the primary cause of corrosion of steel reinforcement. Chloride ions are also present in the de-icing salts we use on our roads during the winter time. Airborne pollutants, as I mentioned, salt-laden sea air, and even some concrete admixtures also contain chloride ions. These dissolved in water permeate sound concrete and reach steel through defects. Carbonation also lowers the amount of chloride ions needed to promote corrosion. And depending on relative humidity, temperature, chloride concentration, wet and dry cycling, etc., chloride penetration can reach 1 to 2.5 inches into ordinary Portland cement in as little as 5 years. And typically we're talking about only a 2-inch cover on reinforcing. So you can see how aggressive this can be in really creating a problem for concrete structures. Freeze-thaw is also a bit of an issue where water is allowed to seep into concrete, where it might freeze and then it expands by about 9% by volume. In moist concrete, this can produce sufficient internal pressure within the pores and capillaries of the concrete to exceed the tensile strength of the concrete. And then we start seeing those cavities dilate and rupture, and ultimately we see scaling and cracking or crumbling of concrete. A couple of good examples there with a sidewalk or a a brown coat over a scratch where water has been allowed to freeze. Effects of high temperature also on concrete can also be destructive, not necessarily to the concrete itself, although the expansion of some aggregates can also create these thermal spalls. But more frequently, it is actually the expansion of the reinforcing steel that creates the internal pressures to overcome the tensile strength of the concrete as well. And prolonged temperatures above 500 degrees C will see the reinforcing melt, and the tensile strength of the entire structure is lost at that point. Plastic shrinkage, this typically occurs during the hydration process, where there's a rapid loss of moisture on the surface, and as a result, tensile stresses between the softer concrete below and the harder drying surface above create some internal stress, and then we end up with cracks propagating through the concrete cross section, as you can see there, to varying depths. And once again, now it's a direct route for contaminants and chloride ions, particularly to start the journey towards the reinforcing. Abrasion, impact, and erosion, also things to consider in our assessment of concrete deterioration. Just the effects of normal maintenance and wear and tear on the concrete surface, such as a snowplow, given the example of that parking garage on the right there, or the constant dripping of water onto a concrete surface is sufficient to erode the concrete itself. Then, of course, the H factor, where humans get involved. And while we can repair much of this damage, we'll always have that cold joint, and that becomes the weak point, or the point of entry for the point of entry for contamination and deterioration to restart. Installation defects, this can occur frequently. The positioning of formwork is critical. Although this is an ICF form, you can see how wavy that is, and doesn't give the reinforcing the entire 2 inches that's normally required in the building code. But through overcompaction, we can see a separation of the larger and the small aggregates, as you see there in the middle, which results in an uneven stiffness or strength across that cross section. A lack of cover, as I mentioned, with the positioning of formwork, really leaves the rebar exposed at the very near the surface. Under compaction, we can end up with honeycombing, bug holes, and things like that. Obviously, reducing our effective cover over reinforcing, but also a gateway for contaminants to start their entrance into the concrete. And ultimately, we end up with things like spalls, but also efflorescence, where soluble salts are washed out of the concrete matrix. So, knowing what we know about concrete now, let's take a look at coating solutions or waterproofing solutions for concrete. And I did put an asterisk there ahead of waterproofing, because I'll in a couple of slides I'll just give you a definition on the waterproofing. So we talk about waterproofing and weatherproofing and damp proofing fairly freely, and assume everybody knows what we mean by those terms, but there is a distinction. But regardless of the condition or quality of concrete, it'll remain both permeable, porous, and subject to deterioration as a result of the presence of moisture in the structure. Chloride ingress, ASR, freeze-thaw, sulfate attack, they all require the presence of moisture to act as a vehicle or to transport soluble ions into the concrete matrix. With moisture being the root cause or key contributing factor to concrete deterioration, in my view, it should be preferred that concrete is treated or waterproofed to protect against that moisture infiltration, either as water vapor, and also protect against CO2 diffusion. And this is the distinction I wanted to make, where we talk about waterproofing. That's the treatment of a surface structured to resist the passage of water under hydrostatic pressure. Damp proofing, by contrast, or weatherproofing, is the treatment of a surface structure to resist passage of water in the absence of hydrostatic pressure. So we really need, it's really in that below grade condition where we talk about waterproofing. And just a little bit of trivia there to understand the extent of what hydrostatic pressure is, or the magnitude of hydrostatic pressure. A column of 1 foot of fresh water exerts approximately 0.43 psi, or the converse of that, or the opposite of that would be 1 psi of fresh water would require a column of water 28 inches high. So the question there is, when we're talking about above grade waterproofing, it doesn't really, it's not really subject to hydrostatic pressure. So yeah, we're really talking about weatherproofing or damp proofing. But as I said earlier, those terms are freely used and are very much interchangeable. But there are certain conditions that separate waterproofing from the other things. So crystalline waterproofing is can be employed either as an admixture or as a surface treatment. These chemicals react with the available water, and crystalline structures develop within the open pores and capillaries and hairline cracks of the concrete to seal against further moisture ingress. Understanding that concrete is full of pores and capillaries, yeah, this now creates an additional growth of these crystalline structures to prevent moisture ingress. It becomes an integral part of the concrete and will continue to react with available water. It's recommended for typically on the negative side or positive side waterproofing, and really limited to use on hairline cracks and not suitable for dynamic cracking. So again, we call it waterproofing, but yeah, if it doesn't have any effect against dynamic cracks, well, it's not really much of a waterproofing treatment in my view. Mineral silicates, these can be incorporated in an admixture as well, or as a topical densifier. When combined with inorganic pigments, these mineral silicates are can also be used as a decorative finish. The silicate reacts with the calcium hydroxide in the concrete to create calcium silicate hydrate. This, much the same as the crystalline treatment we saw on the last slide, fills the open pores within the concrete vacated by the evaporating water. Again, not really truly speaking, not really a waterproofing system, as it will not bridge cracks or prevent cracking. It can produce, when used as a coating, it can often produce an uneven color and finish due to the variations within the concrete mix. It does create a permanent bond with the substrate and has some positive attributes in reducing the incidence of efflorescence. And typically these densifiers incorporate sodium, potassium, or lithium silicate. And just a couple of examples where typical uses you might encounter there on the right. Water repellents. We encounter these usually as silanes, siloxanes. Those are the two most common penetrating water repellents and sealants. They remain vapor permeable, non-film forming. They don't typically transform the appearance of the concrete much beyond its natural gray color. They can be used horizontally and vertically. They do weather over time and do require reapplications as they do weather away. And once again, not a true waterproof system in the strict sense of the word. Silanes chemically react with calcium hydroxide in the concrete to form a hydrophobic layer within the pores and on the surface of the concrete. Really only effective on concrete or masonry, and penetrates much deeper than the siloxane. It does require that calcium hydroxide to react with. Siloxanes, on the other hand, react in atmospheric react with atmospheric moisture and the moisture within the substrate, and then you can use those on non-cementitious materials like clay, brick, and stone. But then we get to my favorite, masonry waterproof coatings. And in my view, there is actually no substitute for a protective coating barrier between the substrate and the elements responsible for its deterioration. Protect against moisture infiltration, provide crack bridging, and doing so, we can also protect against CO2 diffusion as well as chloride ingress. And along with the protective barrier, a coating will provide some aesthetic value. And it's just me, but it's so much more appealing than just uncoated gray concrete. Because of this, coatings will extend the deferred maintenance of a structure and ultimately increase the lifespan of a building. The selection and application of the right coating systems are important to mitigate adverse environmental effects. Compensate for, to some degree, they'll compensate for defects in placement and overcome some of the inherent problems with concrete. Concrete can be a very challenging material or a substrate to paint on, or a material to work with. And as a coatings manufacturer, our challenge is to design a breathable, waterproofing, and protective coating systems to maximize the potential of service life potential of the concrete structure. And it's important to know that not all coatings are created equal, and therefore are vital to understand some of the information presented to us in making the and interpreting that information to select an optimum system design. You know, we're faced with latents or dusting on a concrete surface due to perhaps overwatering of a concrete mix, and that creates a bond breaker right there, as you see on the right. The high moisture content in concrete, 5% and above typically, can create issues with that vapor drive, and I'm sure most of us online here appreciate the blistering that might occur on a coating when concrete is moved into the sun or shortly after coating. And then the high pH of freshly poured concrete or stucco can damage poorly chosen coating systems with alkali burn or saponification, and that example there on the left. And then, of course, our old enemy of efflorescence occurring due to moisture within the structure, liberating these soluble salts to the surface. And to understand the comment about not all coatings are created equal, you know, competition's good, and there's lots of paint and coatings manufacturers out there, and to some degree, paint companies have inherited access to our commercial coatings market. Paints and coatings are quite different. They satisfy two different needs. They're built on the same four building blocks, but I'll expand on that thought a little bit. But it wasn't that long ago that Master Spec really only used paint brands with national coverage. So, and those specifically are Sherwin-Williams, ICI, Glidden, Benjamin Moore, and PPG. Those were the four basics for the Master Spec specification system. In 2003, to give some of those regional paint companies a bit of an entry into this space, they incorporated or accepted that manufacturers with Master Painters Institute qualifications or approvals could also be incorporated into the Master Spec, as well as the four nationals. So even today, MPI, Master Painters Institute product approvals are essentially paint companies. The only two I can detect there, other than those, are MAPEIA and Euclid. So you can see there that index. I think that was copyrighted in 2012, but it's actually the table of contents for the master format of 1995. So, as I said, there are these legacy coatings and painting specifications out there. So we can end up in a situation where the specifiers are now having to put in comments in their specifications like this, so that residential products are not permitted, but then the list of approved manufacturers, acceptable paint manufacturers, well, most of those guys are actually residential paint product manufacturers. And you can see there on the left side where the MAPEI product approval will get you entry into this specification. But yeah, so I think enough said on that. You'll understand that there are paint and coatings manufacturers out there competing now in the same space, and obviously with products of varying quality. And I bring this slide in just as a comparison of a specialty facade coating, specifically for waterproofing and protection of concrete substrates, versus a paint company out there that has produced their own facade coating, and a paint company. And frankly, these are three products that we encounter regularly in facade restoration specifications. And while they are sort of relatively similar in terms of their physical attributes and volume solids, you can see that the higher solids coatings products actually do offer some advantages in terms of higher film build, application efficiency, and a higher film build equals a better film integrity over time. But then we jump down a little bit and start having a look at the performance tests, and you can see there that the manufacturer that's gone to the extra effort of getting it their products independently verified and validated by the Sealant Waterproofing Restoration Institute has a lot more test data to be able to convince you as a specifier that this is the right product to use, rather than trading on a brand name that's been around for a long time and trusting that it will be okay on the day. You can see there that the test data just doesn't exist. So I hope I make the case there that these products have their application, or these paint products have their applications. So do the coatings, but they shouldn't really be confused and attempt to be used on the same structure and expect a similar result. They're really quite two different beasts. You'll see coatings manufacturers will trot out a CO2 diffusion test. There's a lot of science behind this, but really at the end of the day, we're talking about creating an effective carbonation barrier to prevent that wave front from even entering the concrete. And where you'll see a tech data sheet from a manufacturer with anything, an R value, not to be confused with insulation, but an R value in excess of 50 meters. This means that it will prevent that carbonation wave front from reaching reinforcing steel in 60 years. So we're talking a very effective carbonation barrier. To put that in other terms, if you wanted to have give your concrete the same protection as that one coat of or that one application of paint or coating, you'd need to apply something in the order of another 22 inches of concrete as a sacrificial layer to provide your structure with the same protection. Waterproofing and weatherproofing, and really the only test that we offer you is a weatherproofing test, and that is the wind-driven rain test. This superseded the Fed Spec 555B back in 2001, but it simulates exposure to continuous rain at a pressure of 98 miles an hour wind velocity. It's typically just a visual inspection, but some manufacturers will go so far as to present you with a differential weight gain before and after the test, as you see there at the bottom. Water vapor permeance and permeability. And this is a real mind bender. There are 4 different tests: wet and dry cup, as well as the ASTM 1653 and E96. But essentially, the coatings industry has really fallen in behind the ASTM 1653. However, what it does in the first process of its measurement is determine water vapor transmission, WVT, which is grams per square meter per 24-hour cycle. Then a calculation gives you water vapor permeance, and this only measures a rate of transmission or permeance. So to compare 2 coatings, they really have to be of the same thickness. And the calculations within the test of ASTM D1653 doesn't actually go that far. It doesn't actually take that step to calculate permeability. ASTM E96 actually measures permeability, also expressed into perms, but a film thickness needs to be greater than ½ an inch thick, and there are all sorts of adjustments that need to be made, and it really, at that thickness, it's really not a practical measurement for organic paint films. Permeability is the only means to compare competing coatings at different thicknesses. So pay attention when you're looking at the test results for ASTM D1653. Manufacturers should provide you with the perms and the film thickness at which it was tested, because it is a linear relationship. Twice the thickness is half the permeability. So you need to take that into account. Chloride ion permeability. This is a bit of a red herring in my mind and a waste of space, because the test is conducted on concrete, and concrete within the confines of this test, ASTM 1202, concrete already has a very low chloride ion permeability. So when you see a test like this and a manufacturer claiming, oh, well, it has a low permeability class, it really means that, hey, the concrete was doing its job anyway without the coating. Elongation and tensile strength, there are 3 different tests for this, and sadly, not many of these ASTMs were developed with the coatings industry in mind, so we've had to adopt, modify, and apply as we see fit. But you know, the test method and the apparatus are similar, but the results of these 3 tests really can't be correlated. It's strange, though, that SWRI, Seal and Waterproofing Restoration Institute, should actually fall in behind ASTM D412, because strictly speaking, that test requirement is a film thickness at 118 mils, about 10 times the normal thickness of a facade coating or a waterproof coating. And herein lies some of the problems with this, because now the manufacturer or the test criteria has been modified to application thicknesses, where it does actually reflect a real life application. But you're not to know that until you know it. So crack bridging is another interesting one here, and this really obviously an important test from the point of view of concrete. We know it is going to crack sooner or later, and it tests the ability of a coating to bridge dynamic cracks and withstand movement without failure of the coating. There is ASTM 1305 is a pass-fail test that just provides test results at 2 temperatures, freezing and at normal 73-degree Fahrenheit room temperatures, or 75, excuse me. And again, the test procedure it can be modified to suit an individual's ends, but I think it's important here to reference the Construction Specifier magazine article back in July 2013, where they actually assessed the performance claims of 14 manufacturers with their elastomeric coatings that said they all passed recommended dry film thicknesses. They ran a subsequent test and found that really only 9 of the 14 passed at 75 degrees, and even fewer passed at freezing temperatures. So it's there are test biases, no doubt, but there are also test execution bias as well. So SWRI have adopted the EN 1062-7, which is a European standard, and that reflects more, rather than a pass-fail at these two temperatures, it reflects the coating's ability to stretch at 3 different, or bridge a crack at 3 different temperatures. So it gives manufacturers a little bit more of latitude in terms of the displaying meaningful data to a specifier. Flexibility, once again, important if we're talking about concrete and wanting to wrap our coatings around sharp edges, radiused edges. Obviously, the ability of a coating to wrap a smaller angle is and maintain its integrity is much better than something that wraps a larger radius. But typically on data sheets, you're not party to know whether that's a 1/4 of an inch or a 1-inch mandrel that it's passed on. Adhesion testing. It'd be great to know that the products we're specifying actually adhere to the concrete substrate to which they're applied, and it's a great test because it provides you a quantitative result. It gives you a hard number that, hey, it requires this many PSI to remove this coating from this facade. Unfortunately, there are 5 different test apparatus, and a testing bias now becomes a factor in, as a result of the various apparatus that are used. But great again for a comparative test where you have competing manufacturers on the wall, or you want to test the adhesion of the existing coating versus the effects of applying the new coating. But as an absolute number, there's not a lot of frame of reference there. Simulated accelerated weathering. Well, this is the automotive crash test of the coatings industry. We simulate accelerated weathering by applying our coatings to these test samples and exposing them to rigorous weathering cycles in laboratory conditions. They incorporate a high-intensity light source, temperature, humidity, continuous, and we expose these for continuous cycles of up to thousands of hours, 5,000 hours, and actually 7 months in real time. Depending on the failure mode, 3,000 hours in a xenon arc exposure chamber yields similar results to a 60-month exposure in South Florida. And that's a pretty extreme environment with UV, salt latency air, winds, and rain. But not all failure modes are replicated using these simulated accelerated weathering tests. And some of these weathering tests are more aggressive than others. Some are simply a UV light bulb. Others are the xenon arc weatherometers. But sadly, things do change, and sadly, some of our competition are caught out with these changing requirements. Although you can see here, they're still publishing this data even today, 20 years after the ASTM standard has been withdrawn, as accurate and current information on the performance of their product. So something to be a little bit aware of, because certainly those two ASTM tests have been replaced. So in summary, with the selection and application of the right coating system, adverse environmental effects can be mitigated and to some degree compensate for defects in placement to extend and optimize the surface life of the structure. I think I said that at the beginning, and I hope I make that case too. But the term paint and coatings can be and is used interchangeably, and I fall into that trap myself. Except coatings have really become more commonly associated with specialized applications like waterproofing and corrosion protection. Coatings satisfy a much higher performance standard than paint, and have testing credentials to differentiate the product performance from paint. Architectural and decorative paints that you and I use in our own homes are fully matured and commoditized market segment, very few differentiators in the product, and consumers are aligned more by the distribution channel and store type, that we go to the hardware store or the big box store for our DIY product. You'll find the painting contractors will be driven more to the company stores, where coatings applicators or commercial construction guys are working with specialized distribution outlets and manufacturers to provide the right product for that application. Commercial construction is driven by specifications, and these thin film architectural paints simply don't measure up to performance demands. And as Princess was reading my my resume back there, I've been in the industry a substantial amount of time, and yeah, I really do appreciate the differences between paints and coatings these days. In the longer term, substrate repairs and coatings are going to be inevitable, but maintenance can be deferred. And for that small incremental cost in the overall construction budget, a properly designed coating system will protect that masonry construction against the early onset of deterioration for years. Work with trusted manufacturers with credentials in the specific field of application. Manufacturers equally have a great responsibility to the industry to provide reliable and transparent reporting. I get it; they all want to make sales, make a profit, support their shareholders. But if they're not going to tell you the whole story and provide you with the robust system you're looking for, yeah, that's not transparent. So to the specifier, I'll ask you, simply ask the questions, challenge erroneous data, and get a second opinion. Guys in my position will be glad to, even if we're not on the spec, we'll be glad to provide you with perhaps an objective point of view as well. So with that concludes the presentation. Before you'll ring off, I want to thank you very much for attending this afternoon. This does qualify for learning units, both with the AIA as well as any engineers out there with RCEP. So hopefully we have your registration details that we can provide you with the certificates and the credit. So question time. By all means, type in there on your control panel a question, and Princess is going to come to those. Or if something, after we all sign off, if something comes to mind, take down my name, cell, and email address if you like, and I'd be happy to discuss any of these aspects with you in some more detail. So Princess is going to be our moderator here, and I'll hand it back to her to see if they've had any questions.
Thank you, Rankin. That was a really great presentation, a lot of good information. We have a few questions here. I'll start off with this one. Do you offer targeted technical symposiums that would focus on specific product applications for us?
Oh, absolutely. We'd be more than happy to do that. And considering the current environment we're living in, we'd be happy to do that either remotely. We can set up these webinars on a variety of different platforms. We can tailor it to whatever your office needs. We have dozens more of these AIA or RCEP presentations we can also provide if you're looking for credit. But certainly we'd be honored to put something tailored together for your particular office. Glad to do that. And I should actually just jump in there and say, if you'd like a little bit more information about MAPEI coatings, you'll see there on the control panel and our coatings brochure, our PDF, and that'll sort of take you a little bit more into the discussion about facade coatings.
Thanks. Okay, here's one more. Is crack bridging functions of tensile strength and elongation? How much CB is optimum?
Oh, good question. Wow. Yes, crack bridging is a function of elongation and tensile strength. Elongation being the important one, tensile strength being the force required to create that elongation. So the tests are different, but they are related. I should put it that way. When we're coating a structure, we start with, I'm assuming, a zero crack or a hairline crack, and the 1062-7 test, the European standard, does actually start from zero and elongates or expands that crack at a specific rate, and observes for any minor fracturing in the coating. The elongation, the other ASTM test that I referred to earlier, those also expand at a given head speed or a given rate, but usually those the elongation is measured at failure, at complete failure, where the coating sample snaps, rather than identifying a early failure or an early pinhole in the crack bridging test. Very few manufacturers offer that crack bridging data, and more to the point, very few manufacturers offer that crack bridging data that's been validated. So you're not going to go very far to find that there are probably only 2 or 3 manufacturers that offer that. So your choice is limited. But yeah, I think that's probably where I'd leave it. If that individual would like to write to me, I'd be happy to expand on that a little bit more.
Okay, thank you.
Okay.
Here's another question from Carlos. Is there any specific coating for salt front concrete?
Salt front concrete. Is that, did I get that right?
Yeah, salt front concretes. Apparently he works on rebar.
I'm sorry?
He works on rebar and he wants to know if there's a way to add extra protection.
Oh, okay. Well, I think the important thing is when you're doing the restoration is to try and mitigate that the chloride ingress, or not encapsulate any more salt in there. So I don't leave it exposed too long. Make sure it is appropriately sealed or coated. And there are specific rebar coatings. Actually, even within our line, we've got some very good anti-corrosives that can be applied to the rebar to arrest that corrosion. And then, of course, the application of the right mortar to backfill, and then ultimately a coating that will give you some chloride protection. Any coating will give you some degree of protection, or any paint will give you some degree of protection, but a coating will be the way to go. And again, a coating that's engineered for these building facades in these severe environments.
Okay, perfect. And then we have one last question. You mentioned sodium, potassium, and lithium silicates in connection to densifiers and mineral silicate paints. What's the difference?
Another good question. Thanks. I'm going to get a little bit out of my depth when I'm talking about densifiers, but I'll have a shot at this. But essentially, the mineral silicate paints usually incorporate sodium silicates. You may also hear those referred to as water glass. It's a fairly old technology, but useful from the point of view that I mentioned earlier, that they actually create a chemical bond with the concrete. But in the same way as they react and form that chemical bond, so do densifiers. And each of those chemicals, the sodium, lithium, or potassium, work in much the same way. They produce the same chemical reaction, but price is probably the main driver. The sodium silicates are typically cheaper than the potassium or lithium. The application is slightly different too. Sodium, typically you pour that out on the surface, and needs to be broomed and agitated during the reaction phase, and then neutralized and rinsed off. Lithium and potassium silicate densifiers generally just sprayed onto the surface, and no rinsing required. But don't take my word for it. Read the manufacturer's label when you get to that point. But those are really the differences that I understand. I hope that helped. Are you there, Princess?
Yes, sorry.
Oh, okay.
Thank you, Rankin.
Welcome back.
Appreciate it. Although this is the close of the webinar, we don't have any more questions. If you do have more questions, please email Rankin at rjays@mapei.com, or you can reach out to mapeidigital@mapei.com. The webinar recording will be made available and can be emailed out at request. If you signed in with your AIA number, you will receive a certificate in your email. Thank you for attending, and thank you, Rankin, for your presentation.
Appreciate it, Princess, and thank you again to all that attended today. I wish you well. Take care.
Goodbye, everyone.